All right, we're going to go ahead and get started, folks. Thanks for coming to Coast today. My name is Drew Snoffer. I'm the manager of the Data Analytics and Quality team at Ocean Networks Canada. My team is responsible for the overall quality and continuity of ONC's large archive of data coming in. So we monitor things for QA/QC concerns, data quality issues, as well as assessing the data streams. In addition to that, the fun, cool part of what we do is look for problems in our data using state-of-the-art techniques like machine learning. And so Spencer's here today to present the work that we've been doing as part of the Building Bridges project. This project was generously sponsored by the Ocean Supercluster and has built a consortium of organizations to interface with the CEUS organization, which is the Canadian Integrated Ocean Observing System. So I'll say some more words maybe later about ONC, or you can ask me any questions. But for now, I'm going to hand it over to Spencer Bialek to begin the presentation. Take it away, Spencer.
Thank you, Drew. Cool. Hi, everyone. I'm Spencer. I'm a machine learning specialist at Ocean Networks Canada. I was hired a little more than a year ago to work on a specific project, which is finding anomalous data in our underwater hydrophone network. Using I decided self-supervised learning. It seemed like the best method for this task. Uh, and not a lot of people know what self-supervised learning is. I have given some presentations about what it is. A few months ago, I gave a talk about the method that I developed. And this talk is approximately similar. It's a little bit shortened. I'm going to give about a 10 to 15 minute introduction to the work that I've done and the concepts involved. And then we're going to move on to hopefully a somewhat interactive Jupyter notebook tutorial. The interactivity will depend on how many GPU servers we get allocated to you. I was quite surprised to see how much interest there was in this interactive tutorial. I think there was about 80 registrants. So it's going to be maybe a little bit difficult to get a GPU server to every single person, but hopefully most of you will have a GPU server available. So in person, we might need to, I don't know, share some laptops. But in any case, as a fallback, I'll be going through it. I'll be sharing my screen, so you will be able to see how I do the method. And it's always in the GitHub repo. If you have a GPU on your laptop, a pretty sure way of getting this to work is to clone the repo. The URL for that is in the email that you got. And then follow the steps for getting the virtual environment going. I think you need probably an NVIDIA GPU or something like that for that to work. So in any case, just following along on my screen, you will understand a little bit more than when we started. For most people, this is going to be an introduction to using self-supervised learning. For some people, this will be an introduction to using ONC's API for downloading data. And for some people, this will be an introduction to machine learning, to PyTorch, and maybe even Python. So there's a lot of knowledge and skill levels in this session. And no matter what, I hope that no matter your experience level, you will come out of this tutorial having learned something interesting and useful. And please ask me any questions throughout the entire tutorial at any point, because I want to ensure everyone is on the same page and they're all having a good time. Okay. So, ONC has a lot of hydrophones. These are underwater microphones. There are currently 34 active hydrophones on ONC's network all over the West Coast, Vancouver Island, and in the Arctic, I believe, and the East Coast. There's a lot of these hydrophones just listening 24/7 to the sounds of the ocean. This is what a hydrophone looks like. It's from Ocean Sonics. Here's the raw waveform that it's collecting, and those waveforms, those audio recordings, are split into 5-minute chunks. And for every 5-minute chunk, a spectrogram is created. Um, so for these, and a spectrogram is shown here. On the x-axis is time, and on the y-axis is the frequency of the sound. So over time, you get to see the frequency characteristics of the sound, where the brightness or the color is corresponding to the power level in certain frequency bands. So you can tell a lot about the soundscape and different environmental conditions. You can see the calls of whales in these spectrograms, so that there's a lot of information in these spectrograms. Because we have 34 of these, producing these 5-minute spectrograms, we get about 10,000 5-minute spectrograms per day. That's a lot of data. In fact, yeah, since 2006, we've had over 700 terabytes of archived data. That's mostly the raw audio data. But yeah, the spectrograms take up a lot of that too. And currently, yeah, it requires manual review of the data. This has typically been done by one person. Um, and yeah, it's not a very fun task to look through these spectrograms and to note anything that has maybe gone wrong with these instruments. They are sometimes at 2,000 meters below the surface of the ocean. So these are pretty harsh conditions for these instruments to be in, and things can go wrong all the time. So yeah, we needed to develop a more automated method of determining when things go wrong with these instruments so that we can go and service them and also provide that information for end users of the data so they know that the data they're working with meets certain quality standards. So what kinds of anomalies are there? The ones that we were interested in this project were primarily the instrumentation failures because ONC wants to know when their instruments are failing. So you have signatures like tonals, dropouts, data gaps. You have sensitivity issues. We were also interested in flagging when there's vessel noise and when there's rain. You can see this kind of hazy region of the spectrogram, which corresponds to just rain falling on the ocean. Something that we haven't labeled in our data set and we weren't particularly interested in acquiring, but we might with this method still, is signatures like earthquakes, vent collapses, marine mammals. And then there's this big category of like these unknowns, these unknown unknowns, basically. Signatures that we don't know about, but which could still be affecting the instruments, or even like be other features of interest as well. So yes, I also wanted to highlight for the purposes of this tutorial, because you might not be interested in instrumentation anomalies, you might be interested in, say, vent collapses or something else, some sort of whale call. What you consider an anomaly is entirely dependent on your use case. Um, so in our case, sort of normal background soundscape was our normal data. And anything that was kind of different than that, we considered an anomaly. But all of these could actually be considered normal in your use case, and you might be interested in one particular feature in a spectrogram, in which case that would be your anomaly. So it's just, yeah, what is considered an anomaly is totally dependent on your project and your use case. Okay, so we want to know when a spectrogram is anomalous or not. And there are many ways of trying to do this. in an automated way. One possible way is to use traditional supervised machine learning. But there's some problems with that method. First of all, we have a very small amount of labeled data. There's a massive amount of data in general, but some anomalies are quite rare, so it's difficult to manually identify enough of them to build up a sizable training data set for supervised machine learning. And traditional supervised machine learning usually requires a lot of labeled data to perform well, so this is an issue. Second, yeah.
There was one question from the
Oh,
online.
yeah.
Difference between a dropout and a data gap.
Oh, yeah. The difference between a dropout and a data gap. I think so. I think a data gap happens when some of the data has been removed from the spectrogram for purposes of privacy. So usually some sort of military reasons. Dropouts are more like actual instrumentation failures, like the hydrophone just stops recording or records not as well for a moment in time, and so you get this kind of patchy spectrogram. Okay, yeah. So second of all, supervised machine learning, it performs well on data in the same domain. So if you're training on data in this particular domain and your test data comes from the same distribution of data, the same domain, it performs quite well. But if you have data that doesn't look like your training data at all, or even slight modifications, if it's not in the same domain, supervised machine learning can really struggle in these cases. So yeah, this would kind of be like the unknown unknowns in our case. So we have like lots of good training data that we are aware of, but there's also lots of data that we haven't looked at, and there might be some weird things going on there, and that's not in our training data necessarily, so we wouldn't be able to identify those with supervised machine learning. So yeah, it's not looking good for supervised machine learning, but there is a solution. It's called self-supervised learning. So this is a very exciting branch of machine learning. I think it's the coolest one that there is. And it's able to learn information from a large unlabeled data set by creating supervised tasks from the data itself. So this is, a large unlabeled, like in this example, it's just regular images of things, and it's unlabeled. And you have some model that is encoding these images, and you have some sort of supervised tasks that you create. So you can remove patches of these images, for example, and get the model to in-paint, so like reconstruct the missing patches. And you can also do position prediction. So you take a bunch of patches from an image and then get the machine to figure out where those patches came from in the image. So through this process of reconstructing missing patches and getting it to predict where those patches came from in an image, it learns, ideally, some sort of rich information, some rich patterns inherent to the data itself. So it's not identifying anomalies, it's just learning what the data is and creating these like useful representations from the unlabeled data using these pseudo labels. Yeah, and you maybe didn't know this, but you're probably quite familiar with a method that uses this technique. It's any large language model basically out there, ChatGPT. In the case of language, what they do is they mask parts of sentences. Usually it's just like a single word at the end, and then you get a model to predict what that word is. And so that's self-supervised learning because you're masking the data that you have and creating a task from that. And then you can go and fine tune the pre-trained model, which is what the next step is. So you have this, at the end of this, you have a pre-trained model that understands something about the data, and you take that model And then you have a labeled data set that you use to fine-tune the model with this target task. So this is kind of the more like traditional supervised machine learning, where in our case, we're getting the model to predict if a spectrogram is anomalous or not. Um, in the case of like language, this target task could be taking an English sentence and translating it to French. So you need to have like the two sentences corresponding to each other. So that's not a self-supervised, that's just supervised because you need to like curate that data set yourself. Okay. So the advantage of this is that you can, use this, you can use a lot of your data that you don't have labels for. So you kind of give the model a head start in understanding something about your data. So it reduces the need for a large scale labeled data set. You can get very good results using a very limited amount of labels, much better performance than supervised machine learning because you leverage the data's inherent structure. And yeah, it's been shown in numerous studies that um, self-supervised learning is better at understanding data, not in the labeled data set. It can generalize a lot better. One of the papers that I was inspired by with this method was a paper in radio astronomy, where it was essentially the exact same setup. They had spectrograms from radio signals, from radio telescopes, frequencies, it's light, so light and sound are both represented as waves. So uh, uh, you can visualize the data in almost the exact same way with a spectrogram. And they were also looking for just anomalous signatures in these spectrograms. These are, instrumentation anomalies in their case as well. And yeah, they found that with self-supervised learning, they were finding like if they could find the unknown unknowns, essentially these things that they hadn't labeled in their data set. And that's been shown over and over again that self-supervised learning is capable of doing this. Yes.
Could you just explain one more time that you have the first step where you have this pre-training model and you were
Yeah.
talking about having it assemble patches of images and things like that.
Yeah.
What was the second step or the second part?
Yeah, so you
Question.
Oh yeah. There's a question here about just repeating the process of going from this pre-trained model to this fine-tuned model. Yeah, so the pre-training, it's usually you have like a very, very large data set. In the case of like ChatGPT, it's millions and millions of text tokens. And you have these self-supervised tasks. You train it. It takes a very long time typically. And then at the end, you have this model that can take a sentence or an image and encode it. And that encoding turns it into just a vector that contains an abstract representation of the data, but it's like a useful representation. And then so you take that pre-trained model, which is already doing this, already understands something about your data, and then you feed in a regular data set with labels. So in our case, it's spectrograms with labels that we have selected. Like this spectrogram is anomalous, this spectrogram is normal. And you feed that data in a supervised setup. So your target task is trying to get the model to predict if your spectrogram is anomalous or normal, and then you train that model, which is this model. So the weights change slightly in this fine-tuning process, but the base pre-trained model is where you start from. Does that make sense?
Yeah, thank you.
Cool. Okay, so this is the specific model that we are using in this project. It's called Self-Supervised Audio Lambda. You can find the paper here if you want to get into the details. It's a lot of computer science, and I'm not going to get into the intricacies here. But this is essentially what we have in our pre-training step. We have about 10,000 normal spectrograms, just regular background soundscape. And we turn the spectrogram into patches. We mask some of the patches. We feed that through this encoder, which is the model. And out on the other end is where we have our self-supervised tasks. So again, we're asking the model to reconstruct these missing patches using the context of all the other unmasked patches. So it understands kind of the structure of the spectrograms. And then, yeah, this position classifier, we're getting it to predict where in the spectrogram these masked patches came from, again, using the context of all the unmasked patches that went through. So yeah, we run that, get out this pre-trained encoder, and from this pre-trained encoder, we have about 6,500 normal and anomalous spectrograms, which we again patchify these spectrograms and fine-tune this pre-trained encoder either with a binary classification task, anomalous or not, or we can even predict exactly what kind of anomaly or anomalies are in the spectrograms. But for the purposes of this tutorial, what I'll be showing you is this binary classification we're just doing, whether it's anomalous or not. So the data that I used in this study and the data that we'll be using in the tutorial comes from hydrophones at various locations, various depths. So you get a variety of different soundscapes, like Endeavour is very quiet. It's at a very large depth in the ocean. You might have a lot more ships, for example, in the Burrard Inlet or the Strait of Georgia. So yeah, the soundscapes that you see in these spectrograms vary quite a lot. And yeah, in total, we have about 13,000 spectrograms, which represents about 45 days of audio data. Most of the data is normal. There's lots of ships. And then, yeah, not so much of these other types, which have some interesting labels sometimes. Just like, yeah, we didn't know what this one was. We just called it anomaly. And then there was another one that we didn't know exactly, so we called it unknown feature. But yeah, and it corresponds to about a few years of data as well.
This is for training.
This is for training. Yeah, we curated this data set. One person mostly actually, Herminio. I don't know if you're here, Herminio, but Herminio looked at thousands of spectrograms. I made an app for him to look at the spectrograms and label them, which we'll be using in this tutorial to label these spectrograms. But yeah, he spent many hours looking at spectrograms for this project. Thank you, Herminio. Yeah, and so the results we get out of this are pretty good. We have for identifying anomalies, we have a 97% precision, and we recover 99% of the anomalies in our test set. We have, yeah, these are the normal samples, so things that we have predicted as normal, which are actually normal. These are the true anomalies, so things that we have predicted to be anomalous and are actually anomalous. And these are like the what we have predicted to be anomalous, but which we had labeled as normal in our data set. And I looked more closely at this category, these false positives, and I found that our model was actually finding that they were anomalous. And for whatever reason, I did some of these labels as well. We had labeled them as normal in our data set, but the model was doing better than us at identifying these anomalous spectrograms. So we actually probably get better statistics than this, which is already very good. Yeah, so this is just the performance by anomaly type. I just picked out a few of these anomaly types to show this interesting thing I did here where I wanted to test the generalization capabilities of this model. So I removed the dropout anomaly type from the training set. So in that second fine-tuning stage, I removed this dropout category. So the model never saw dropouts. And despite that, it was still able to identify and get 97.2% of the dropout type of anomalies. So this was just a simple experiment showing that we were able to, yeah, find anomaly types that we didn't put in the training set. So running this model on new spectrograms, ideally, we'll be finding anything that stands out from the background soundscape. And then that information will be fed to an expert, and they'll be able to label exactly what kind of anomaly was picked out by this method. And over time, the model will improve.
I guess like the dropout is also the least subtle anomaly that
Yeah.
one could imagine.
Yes, exactly. Yeah, it definitely stands out. Yeah. Yes, so the future work, the plan for this is to implement directly on the ONC servers so that we don't need to have a person looking through 10,000 spectrograms every day. Only the ones that we pick out with this model. And then, yeah, that information will be given to an expert who will verify yes or no what kind of anomaly is in these spectrograms, which will be fed back into the model to retrain it and get better predictions over time. And we'll be expanding to more hydrophones, and that will just require more labels and more instrument types. So ideally, this method will just be used all throughout ONC for finding anomalies and helping out everyone. Oh yeah, this is we're here. This is from an old slide deck. Yep. So congratulations, we're here. Okay. Yes.
I have a quick question. Like, what are presumably the downsides of the unsupervised? They're just like cost and compute power.
Yeah.
Repeat the question, please.
Yeah, the question is one of the downsides of the self-supervised learning is probably just the computational cost. And yes, that is one of the downsides. Although in this case, the audio Mamba method or architecture that I was using actually doesn't use that many compute resources, so it's kind of light. Yeah.
Like, do you know approximately how much it costs to like run your training sets, or like is that an easy number that you're?
Well, it took. Sorry, Drew. I will. Yeah, the question is how do I know kind of how many computing resources, what the computational cost was when training my method. And I don't have an exact number. I was using I was using the NVIDIA 4090, GTX 4090 on this laptop for some of the experiments, and it took like a few hours with 10,000 spectrograms. So it takes a while, but it's not like outlandish. Yeah. Yep. Yep.
But they have like not the same as a representation of like anomalies for like is there a problem and you have, for example, and there are so many samples to that soil. Like is the representation of the sites equivalent to like is it mixed well in your representation of signals? Or is like some sites have like more noise? Like is it difficult to train the data for a specific site when you don't really have samples from that site on samples from another site? Does that make sense?
Yes. Yeah. The question is the question is with these sites here and these anomalies, like what's the distribution of anomalies for each of these spectrograms? Like, do some of these spectrograms just only have engine noise, maybe, or so the hydrophones? Some of the hydrophones only have engine noise. Do some of them only have data gaps, or are they kind of well represented throughout all of the hydrophones? And the answer is definitely that it varies. For example, Endeavor has almost no ship noise. And yeah, some of them have kind of unique anomaly types. And so, yeah, the performance on each spectrogram, on each hydrophone, can depend a lot on the anomaly type that you're going for. But like so I would say this was kind of a limited data set, just because it's hard for one person to generate a large data set. So using this on new spectrograms, it should still be good at finding anything that sticks out from the background, and getting more of these types of anomalies for each spectrogram is ideally what will happen over time. But yeah, yes, that is one thing that we have to keep in mind for sure, is that some of them will be rare for some hydrophones.
Is it okay to ask more questions?
Yeah, yeah.
So, maybe it's just because I'm an expert and I don't want to be made redundant, but my question is like, can you engineer I guess like typically you do kind of like feature engineering. So like, is it possible to like, in addition to the spectrogram image, you might put in some features that like somebody who knows hydrophone data, maybe says like this is like a good feature, let's say like the overall signal strengths across like all frequency or like some frequency, can I say, oh, this is probably something that gives you like a lot of bang for like a single number? Can you add that like expert engineered feature to make the algorithm better?
Yes, the question is, would it maybe improve the performance of our model to include some expertly crafted features of the data? So someone who knows a lot about spectrograms might know how to, or audio data might be able to extract some very important features that a model could use to pick out different anomaly types. And I mean, so yeah, like you said, you don't want to be made obsolete. And that's why one of the reasons why machine learning was even created in the first place is because we were using these hand engineered features for understanding and predicting things about data. And it turned out that neural networks and other architectures were just so much better in a lot of cases at just using the data itself. But I also have seen a lunch and learn talk at ONC where someone was using like the entropy of an audio signal to determine when there were man-made artificial signatures in spectrograms, and he was able to find ship noise with like an extreme like precision. And so I will say yeah, I think it could help. I don't know which features would help, but yeah, that's definitely worth looking into to improve the performance and find maybe some rarer types of anomalies. Okay. Uh, whew. Okay. Alex, how's it looking with compute servers?
It's tricky, and I think you're gonna have to explain how to connect to the notebooks.
Oh yeah, I definitely will.
Or those can be started up.
Yeah.
Just before we move on, Spencer, there's a couple of online questions.
Oh, yeah, sure.
First, would this approach work with time series data points?
Yes, like if it's 1D time series, that's basically like how large language models are trained. So I'm not like fully aware of the self-supervised tasks that researchers use for time series data. I know that it happens, but yeah, it's kind of like text. So I know one of the tasks would just be masking certain parts of the time series data, and maybe even the same kind of location prediction self-supervised task. But yeah, I know that masking and like reconstructing masked patches of the data is always a good self-supervised task. So the answer is yes, it can work on time series data.
Okay, thank you. And then how do you define quiet or silence? Is it the same for any area?
That's a good question. Definitely not, it's not the same for every area. Some locations are just kind of constantly noisy, with ship noise. Some areas, experience more rain, different kinds of weather. Some places have, yeah, just like more human activity or even more just biological activity. So yeah, the background soundscape is completely dependent on the location, and can change quite drastically, such that some spots you'll have, like 70% of your spectrograms will contain ship noise. But that's, yeah, still useful data to collect.
Okay, and then finally, this was asked before and you did answer it, but just as like a kind of final overview before we dive into the model. What's the difference between a dropout and a data gap? This might be useful for those that haven't necessarily spent a lot of time with hydrophone data.
Right. Yeah, so these are just kind of two types of data where either you're like completely missing chunks of the data, or they just uh, they kind of stand out from the rest of the spectrogram. Either, yeah, the hydrophone has stopped recording or has started to kind of malfunction sporadically, and the signal coming through is decreased a lot. So it's just like these like stark contrasts in the spectrogram.
Okay, thanks. That's all for online.
Cool. Okay, yeah, so we'll move on to the somewhat interactive tutorial from here. Let's see. Okay, so if everyone can go on to the CoCalc platform, you will see if you go to the home page here on your Explorer, you will see you won't see exactly this, but you will see this ONC SSL tutorial. I think that's probably all most of you will see. So just click through on that, and then the GitHub repo. I've already cloned it into all of your projects. Yep.
It might also be called self-supervision anomalies, ONC. Oh, it changed.
Yes. Well, it depends where you access it from. But if you go to home, you should see ONC SSL tutorial, and then yeah. And so if you click through on that, you will see a notebooks folder. So click on the notebooks folder, and then this notebook, the interactive hydrophone anomaly workshop local notebook. Click through onto that. Yep. Yes, so this is where it's going to get a little clunky because not everyone is going to have access to a GPU, and I don't believe this will work completely without the kernel that I have created for everyone. But what you want to do first is, if you do have a GPU, a GPU compute server on the CoCalc platform, you want to click on this server button. Once you've gotten into your notebook, you want to click on the server, and you'll see this this interactive tutorial GPU if it's available to you. And you want to click on that. And once you've gotten that server selected, there will be an option for this ONC tutorial kernel. You might need to refresh the kernel list. But once it's in there, you will see it. You can select it. I'm wondering if anyone in here, yeah. Okay.
That's where I am. And then it says. No, it's just like what I didn't have it. So,
Okay.
yeah, so it took me a while for anyways, but not there.
Great. Yep.
Walk through those steps that you just did one more time?
Yeah, of course.
Because, some people on the line, like me and others, missed one thing and were lost.
Yep, for sure. Yeah, I will run through these steps again to ensure that everyone's on the same page. So if you go to the CoCalc platform, And I think the first view that you see when you log in is like a project that you want to click on. It's like the self-supervised tutorial project. And then once you get to this screen, you want to click on the home button. Once you're here, you will see an ONC SSL tutorial folder, which you will click through on. You'll go to self-supervision anomalies ONC.
This is where they.
Which is the GitHub repo.
I got it.
And then once you are there, there's a notebooks folder. There's a lot of other stuff in here, but yeah, you'll find the notebooks folder, hopefully. And then in the notebooks folder, there's the interactive hydrophone anomaly workshop local notebook you'll click on. 1 second. Okay, so the error.
So now when I refresh, then I guess I can. Oh yeah, the other tab for your projects. You go here. Okay.
Yeah. And then.
Oh, it's just already open. Thanks. Up here. Okay. Yeah. There we go. Oh yeah, and then I got this. Okay, just press the next here. Okay, so yeah, started. Yeah, we're trying to get the compute server started, but the too many people.
It's a lot of people, and getting this many GPU instances started might take a little while. But I know, some people's compute servers have started, and I guess we just need to wait for the others. But while people are waiting, I will run through the tutorial, and we'll be able to see all together what is going on. And yeah, I'll explain all the steps as clearly as I can. Yep. So that is if you don't have a compute server, that is what you should expect. But if you get onto the notebook, the first thing you should do is click this server button, and if you have a compute server available, if it has started for your account, you'll be able to select it. And then once you've selected it, the kernel that I created, called ONC tutorial, should be available in this kernel drop-down list. You might need to click refresh kernel list. But again, yeah, the first step is clicking the server button.
It's fine, I just watching. So like no. Maybe this is what other people are seeing, like how this server doesn't show up.
Yes. I will try again. Yeah, so in the worst case, you just have to watch me go through it. And if you have a GPU on your laptop, or if you have access to a GPU on a server later, you can run through this notebook as well.
But you need to run Linux, right? Or
you might need to have Linux, yeah. But I have a Windows laptop, and I'm using the Windows subsystem for Linux, so it works on my Windows laptop. Yeah. But I don't think it'll work on Mac. Some of it will work, but running the actual self-supervised model will not work. You need Linux to get the specific package, Python package that I'm using. Okay, so yeah, to reiterate, this is this notebook is available in the GitHub repo, so you'll be able to find it and run it later if you have access to a GPU. The goal is to gain some experience with self-supervised learning and seeing how it works, seeing how it can be better than supervised machine learning. We will process audio data. We'll download some from the ONC API and process it. We'll label it with the labeling app that I have created, and then run some experiments with that. And so again, lots of different knowledge levels available in this group. So I will try to walk through this to accommodate everyone. So the first part, the notebook is split up into two parts. We have supervised versus self-supervised comparison. So this is just kind of showing the strength of the self-supervised method. And then we'll have a break. And hopefully during the break, we'll be able to diagnose some more issues with the compute servers. And then, part 2 is going to be building the ONC dataset and fine-tuning it and working with that. If you are able to run this notebook, and you never have before, basically you can hold down Shift and press Enter on cells to execute them. Or there's also in each cell, there's this Run button. You can click Run. So that is how you execute the code. There's also markdown cell blocks, which contain text only, like this one. So that's just kind of a primer on notebooks and the structure of this tutorial. We have a table of contents, which you can click through on to get to the various sections. In case you get lost, you can just kind of come back up here, click on table of contents. Okay, so this notebook was kind of intended to be used not only during this session, but also for people later who didn't get my introduction to all these concepts. So I just lay out what self-supervised learning is, what anomaly detection is. So just kind of an introduction to the concepts here. And so the workflow that I did for this project and in this notebook is downloading audio data or spectrograms from ONC, pre-training a model on that data, and then fine-tuning it and evaluate it. We already saw what a spectrogram is. Samba is the self-supervised audio Mamba model that I used for the self-supervision architecture. And then, fine-tuning, which I explained. So this is, another example of a spectrogram. So we have time on the x-axis and frequency on the y-axis. So you can see lots of different sound characteristics in the spectrogram. So if you are, just some setup instructions again, mostly for people who are learning this locally and not through this CodeCalc platform. And then if you're running this locally, you will want to uncomment these lines so that you can download the data that we'll be working with in the tutorial. But yeah, if you're accessing this through the CoCalc platform right now, which some of you hopefully are, then just skip those cells. So yeah, the first cell here is just importing Torch, all the necessary packages that we need. PyTorch is a Python package that was made specifically for like harnessing the power of a GPU for machine learning purposes. It's a very widely used Python package in the scientific research community because it's really easy to construct like neural networks and other kinds of machine learning models. So PyTorch is what we're using. So yeah, luckily I got access to a compute server with a GPU. So I am able to run this right now. Yeah, so we have everything accessible. I do. Yeah, so the next cell is just setting up all of the directories that we'll be working with. So you won't need to change anything in this cell. It's just setting up all the directories and pointing to where the data is stored. Yep. And then we make sure that the repository is on the system path so that we can actually use the code and the logic that I put into the GitHub repo. Okay, so that's all the setup is just defining all these variables. Yeah, so we can finally move on to part 1, and we're at 10:05. Great. So yeah, we're doing a comparison here between supervised and self-supervised learning. So we're going to be training a convolutional neural network, which I'll explain what it is for those who don't know in a second, as a baseline. So this is just a traditional supervised machine learning. This is a kind of model that most people would use in this case. And then with the same data, we'll be taking a pre-trained self-supervised model, one that I have pre-trained already, and fine-tuning it on that same data set that we used to train the CNN, the convolutional neural network. And then on the same test data, we'll compare the results from each one. Yeah, so yeah, the idea here is to just give you an intuition for the strength of using self-supervised learning when you have a small labeled data set. Okay, so more imports here, making sure we have everything ready to go. These dataset means and standard deviations are just for normalizing the data, and I got the mean and standard deviation ahead of time. Yeah, so I have the full data set uploaded onto my compute server, and hopefully those of you with compute server access at this point will also have the full data set on your compute server. So this cell just opens up the file. It's an H5 file, which is just a kind of file format that is useful for storing data and associated metadata with the data. So this H5 file contains all the spectrograms that we used in the study, along with all the labels and the labels are just like the anomalies, the anomaly types that we labeled in the data. So yeah, we have 16,500 samples in total, and then it just shows all the different labels for all the spectrograms. Some of them have multiple labels. And then we visualize some of the samples. So yeah, you can see that a lot of them are very obvious. Probably, sometimes you don't even necessarily need machine learning to identify some of these anomalies. But then some of them are a little bit more subtle, like rain. There's these tonal features that appear sometimes, and they're quite faint often and difficult to detect. Lots of ship noise. Can't see any ship noise, but I'm sure there are. Yeah, engine noise. Engine noise. This is a very clear engine noise signature, where the frequencies kind of go down over time and then go up, which is like a Doppler shift as the ship is passing by the hydrophone. This one has lots of tonals. This is a sensitivity thing, where it's very loud and suddenly not. So yeah, you can kind of just take a look at those spectrograms to get an idea of the data set. And then from that full data set, we split that data into a training, validation, and test set. This is kind of standard operating procedure with any machine learning setup. So that, basically so that we aren't cheating and getting results that are completely false. And we want to build a robust model that is not overfit to the training data. So if you are overfit to the training data, then if you shove new data into the model, it will just be awful at predicting things that you care about. So 80% of the data goes into your training set. This is the data that is used to train the model. 10% goes into a validation set. So you, after you shove in all of your training data, you get the performance on this validation set that you hold out. So you don't use the validation set to adjust the weights of the model, but you test the performance of it after every time you shove in all of your training data. You analyze the performance on this validation data, and over time, as you for every epoch, which is an epoch is once you've put all of your training data through the model, and then your validation data afterwards. That's one epoch, and after every epoch, you get your performance on your validation data, and you track that. And after every epoch, ideally, the loss on your validation set goes down. But then, and your performance on the training data also goes down, which corresponds to your model learning. And then eventually, the performance on your training set keeps decreasing, and the performance on your validation set starts to get worse because your model is overfitting to the training data, and so your performance gets worse on this validation data. And that's when you stop the training. So you track the performance on your validation data. And usually I just collect the model, the epoch where the performance on the validation set is at maximum. And then, we hold out 10% for a test set. So once we have fully trained the model, you use this test set to just see its performance on the data. Yes. Yeah.
If you brought out examples in the report that data set here, I don't see the drop down.
Sure. Were you unmuted for that? Or should I repeat the question? Okay, cool. Yeah, so some of the dropouts are actually quite. Oh yes. Okay, so the question is, can I point to specific examples of a dropout occurring? And yeah, so some of the dropout features are actually quite subtle. It might just be like one column in the spectrogram that's affected. which actually does happen quite often for some reason. It's like 1 or 2 columns, which is kind of hard to see on the spectrograms, just looking at them. So yeah, sometimes Herminio had to go expand the view of the spectrograms and do some more intricate analysis on each one. Some of them, like for example here, I believe, yeah, it's a little bit more obvious. But yeah, sometimes the features are quite subtle. Yeah, so yeah, the training, validation, and test sets are very important in machine learning applications. I have seen, unfortunately, too many times people training models incorrectly by, not using a validation data to track the performance of the model over time, and then you just get this model that's overfit to the training data, and they get amazing results on the training data, and they say that the model is good, and it's just not true. So if you're doing any machine learning application, please ensure you stick to these 3 data sets. Yeah, as a base. It can get a little bit more complex than this, but just as a base, please do that. Okay, so yeah, this is where we do that. We take the full H5 file and split it up into training, validation, and test data. So the training set has 13,200 samples. Validation is 1,650. And then yeah, we use this seed. I also wrote that here, but for reproducibility's sake, we use a seed value of 42, so that every time we create this training, validation, and test set, we get the exact same data out, so that we can be sure that we can reproduce the results exactly. Okay, so for the purpose of this tutorial, I created a small data set based on that large data set that I have made available to everyone. For a couple of reasons, doing any training or inference on thousands and thousands of spectrograms can take a little bit of time. So I wanted to kind of speed that up. And also just to kind of force some anomaly types to be small in quantity, can like more easily show the strength of self-supervised learning over supervised learning. So yeah, I created a small training and validation set from the large data set, and then the test set from the large data set I just set aside, so that the convolutional neural network that we train and the self-supervised model that we fine-tune on the training data, we can test both on this holdout test set and compare the results 1-to-1. So yeah, we collect a limited number of normal samples and a limited number of anomalies for each class to create the small data set. So if you are running this live with me, you don't need to execute this cell. It takes like a couple of minutes, so you can run it if you want. But I also have the data loaded into the compute server. So I've created this already and made it available to people. So I'm going to skip this cell for now. It's just so we don't have to wait for a couple of minutes. Okay, so yeah, we have this small H5 data set that we can now train some models with. So how do we train a model? There's a couple of steps that you need to do with PyTorch. So the first step is we create a data set class. And this is just how we tell PyTorch how to load the data so that it understands kind of the structure of how your data is saved and how to collect spectrograms with their associated labels so that we can use that later on to train a model. So yeah, the dataset class tells the computer how to get a data sample. So in our case, we have this HDF5 file. So we tell in the dataset class, we tell it that that's where our data is stored. We tell it how to access a spectrogram from that file. We normalize it, which is like somewhat important in most tasks just to standardize the range of your data. And then, yeah, the dataset returns tensors. Tensors are just these data types that PyTorch uses. They're essentially matrices that are, yeah, they're objects that a GPU can understand. So we return tensors. So this is what the dataset class looks like. You initialize some parameters. In this case, I'm giving it the path to the H5 file. I'm telling it what the split was so that it knows what the train and validation data are. Oh yeah, so the split is actually saying if it's the train or the validation set. I give it the dataset mean and standard deviation for normalization. And then, yeah, this is opening the file to get all the indices and labels. So yeah, if you're bringing your own data for this method later and you're using an H5 file, this would be like a pretty standard way of setting a dataset class up. So this is where we just get the label for the spectrogram. It's either going to be a 1 or a 0. 1 means that it's anomalous, 0 means that it's normal. So here I'm just saying if the sum of the labels, so it's every spectrogram has a vector of zeros and like a binary vector essentially. And the position of every number corresponds to a specific anomaly. So say if it has engine noise, it might have a 1 in a specific place in that vector. If it has a dropout type, it has a 1 in a different spot. And so yeah, that vector just tells the dataset class which anomaly type it is. And so if the sum of that vector is greater than 1, it means that there is an anomaly. So that's how we get that's how we define the output label that we're trying to fine tune on. It's either a 1 or a 0. So, and yeah, and this get item function just collects a spectrogram, normalizes it, transposes it, just changing the shape of it to be ready for ingestion into the model, and then just returns the tensor and the so the spectrogram and the label for it. So yep. Yep.
So means that it's basically looking at the background of one of the spectrograms and bring everything to the same level.
Yeah, well, so I calculate the mean and the standard deviation of the entire data set of spectrograms that I have, and then use that to create for the whole data set, ensure that the mean of the data set is 0 and has a standard deviation of 1.
Well, you're not working with images, but with the numbers representing the images, right?
Yes. Yeah. I'm working with MAT files that ONC provides. So they're just, yeah, it's just a matrix of numbers. Yeah. Yeah, the question was how I'm doing the normalization. So hopefully that was clear. Okay, and then the other thing that you need once you have the dataset class is a data loader. So the data loader takes the dataset and bundles it into batches of spectrograms. So we shove 4 spectrograms at a time into the model. A data loader is just like a standard, again, PyTorch thing. You're just telling the computer how to feed in the data. Once you have the dataset class, you know how to access the data, and then the data loader is telling you how to load the data into the training procedure. And then another kind of standard thing when you have a very imbalanced data set, like in our case, where we have a lot of normal samples and not that many positive examples or anomalous samples, is to use a weighted sampler during the training procedure, which forces the data loader to pick anomalies more often during training. So the model can see more anomalous sounds. Because the problem is, during the training procedure, if you don't use this weighted sampler, a lot of these batches are just going to be only normal samples. So the model can get lazy and just guess normal every time and get like a perfect score. And so that's going to really bias your model to only predicting normal as the class. So that's why you want to use the weighted sampler, which is just like pretty standard in any machine learning setup. But again, something that people miss a lot if they're not familiar with using these things. So yeah, throughout this tutorial, I'm trying to use it as an introduction to just machine learning and like standard operating procedure with just any machine learning, and then also introduction to self-supervised learning. So it covers quite a lot. Okay. So yeah, building the data loader here. So yeah, we define the batch size and the number of workers. So this is how many parallel processes are used for loading the data. So if you have a lot of CPUs, that can just make the training procedure faster because you have more processes like collecting these batches and preparing them for ingestion into the model. I'm just using 4. Sometimes you only want to use 1 if you don't have a very powerful laptop or computer. Yeah, and then this is how we define that weighted random sampler. Define the data loaders finally with that sampler. And then creating the test loader set as well. Yeah, so here's the dataset class for the full test set, and then creating the data loader for that.
Would they set the loader to 1 and will run? Would this take longer?
Even without a GPU. For people running this locally, can they set the number of workers to 1 if they're using a CPU? And again, the answer is yes. Even with CPU, you can have this, I think, be not just 1, it can be 4. It just depends on how many CPUs your computer has. And if you are running this locally with just a CPU, and you have PyTorch in your virtual environment, like all of this should work, again, except the self-supervised learning part of it. So we have the small data set that we've created. We have our train data, we have our validation data. So we have some normal and anomalous samples in the training data, and the same with the validation data. And these are the weights for the weighted random sampler. So for the anomalous samples, we're sampling them much more frequently, or yeah, just ensuring that we sample approximately the same number of anomalous and normal samples for each batch. Okay, so this is where we define the convolutional neural network. This is, yeah, a standard kind of architecture for when you're working with images. And a spectrogram is essentially an image. And yeah, we have these convolutional layers, which look for features like, yeah, lines or curves or specific patterns in the images or the spectrograms. We have this rectified linear unit layer that kind of turns this into a non-linear learning operation. So for learning any patterns in the data that are non-linear, which is very important because most of the data that we're working with, all of it, yeah, it's non-linear. It's not linear. Okay, and then we have these pooling layers that shrink the images and help the model focus on the more important standout features. So this kind of just creates, it just collects the maximum values that have been picked out by these previous layers. So the ones that are kind of most important. And the final layer just outputs a 0 or a 1. And then we have a loss function, which compares your prediction, which is a 0 or a 1, or it's kind of a continuous value throughout that range. And then we use a threshold to define it as 0 or 1. And then we use a cross entropy loss to compare the prediction with the actual known value that we have already curated. And then if the prediction doesn't match the actual value, then the loss is high, and through back propagation, which I'm not going to get into that too much, but we can understand kind of which weights in the model are contributing the most to this incorrect prediction and adjust them through this process called back propagation, where you back propagate the gradients of this model. So like a neural network at its core, it's just a bunch of calculus and a bunch of linear algebra, and you're just calculating how much each weight is affecting the output of your model, and you are adjusting those weights over time throughout this whole training procedure until you get a prediction that more closely matches what you know the truth is. And so that is all calculated in this loss function, which, yeah, helps the model over time learn more how to predict the real known answer. Yeah, so this is this convolutional neural network that we define in PyTorch. So it's just a bunch of convolutional layers, again with this rectified linear unit and this max pooling layer. Again, this is all just like very standard stuff. If you look at any like PyTorch tutorial, it'll show you basically the same thing. Yeah, and so we create that. We're using a CUDA device, which is good. That allows us to use the GPU. Okay, so then we do the training procedure. We're at 10:30, so I've already trained a convolutional neural network before this and made it available as well. So if you are following this live, you can also skip this step because it takes like 10 minutes to train this CNN. So not a terribly long time, but I don't want to just kind of sit here. Like during the break, I think I'll get it training. But yeah, So I already explained the training procedure where we feed in batches of data, calculate the loss, and update the model weights to reduce the error. I use the validation set to track the performance of the model over time, and then just keep going through an epoch at a time where we feed in the training data and train it. And so I've already trained it, and I'm just going to evaluate it on the test set. Which takes a minute. Okay, so this is the confusion matrix that comes out from that. So it's like it doesn't do a terrible job. Again, these are the true positives. Yeah.
Explain what a confusion is.
Yes, yeah, I'm going to. Yeah. And I also talked about it in my intro slides, but yeah. So this is the spectrograms that we have predicted as normal and are actually normal. And you can see that we're doing well here with the CNN. And these are the actual anomalous spectrograms that we have also predicted to be anomalous. These are, again, the false positives where the model is predicting anomalous, but the data is actually normal. And these are the false negatives where the model is predicting normal and it's actually anomalous. Yeah, so it's doing a decent job. So like, supervised machine learning isn't terrible at this task, but there are limitations to it. So yeah, yeah, I will not forget.
Okay, that's fun. How do you define malfunctions?
Yes. So the question is, I chose 20 epochs for the training procedure, and just like through my experiments, I found that was enough. You can do less, you can do more, because what this training procedure does, this is what I usually do, is at the end of every epoch, I calculate the performance on the validation data set, and if the performance is better than the last one, the last best performance on the validation set, I save the model as the best model. And so no matter what, so if you train this for like 3,000 epochs, you will still get out the best model. The one danger is like doing too few epochs because then you might not get a well-trained model. So usually when you do these sorts of things, you want to do some smaller experiments with not too many epochs to just see how your training loss and your validation loss are performing over time, and then just like choosing a number of epochs that you know that you can get a good performance on your validation set with.
Right, so if
Yeah.
the your back propagating the back making the error and basically minimizing your error in each epoch, is that very good?
Yeah, so the question is, at the end of every epoch, am I using back propagation to change the weights of the model and correct for the error? The answer is yes. Yeah. Okay, so I evaluated the CNN. We also have the self-supervised learning model, the fine-tuned one. So these cells, I'm just gonna quickly go through these because we're at 10:36 here. But yeah, so again, I've already fine-tuned this model and made it available, so I don't have to execute this training. Specifically this cell right here. Again, it takes about 10 minutes, so I'm not going to execute that. But during the break, I will. And if you are also following along, you can train this during the break. Okay. So this is doing the same thing as the CNN, where I'm just evaluating on the test set, the same test set, using this fine-tuned Samba self-supervised fine-tuned model. And yeah, the inference time is about the same as that simple convolutional neural network. And I think that's one of the strengths of this particular model, this Samba model. I chose it because the inference computational cost was very low compared to other sort of self-supervised architectures. Transformers if you've heard of those are another kind of standard architecture, especially in self-supervised learning. Transformers are what are the backbone in ChatGPT and most other large language models, but there's these state space models which are an alternative to these transformers, and that's what this Samba model is. And it tends to just be really computationally efficient when you're doing inferences. Okay, so here's the confusion matrix for that. We improve. We have fewer false positives, more true positives, and true negatives and true positives here for the anomalies. So just doing a quick comparison again, we had 80 false positives with the CNN. So and 37 for the self-supervised learning. And that's, the fine-tuning actually uses like the fine-tuning step uses an even smaller convolutional neural network attached to the pre-trained network. So with even a simpler convolutional neural network, the power of this like pre-trained self-supervised learning model really increases the performance. Okay, so the last thing in part one is just comparing the performance of those two models. These are, again, just some fairly standard types of metrics and analyses that you do in machine learning tasks where you're making some sort of binary prediction or some sort of classification. So an ROC curve and a precision recall curve. So yeah, the orange line here is the Samba model. The blue dashed line is the CNN model. And essentially, you have the false positive rate on the x-axis here. You want that to be as small as possible. You don't want false positives. And the true positive rate on the y-axis, you want that to be as high as possible. So essentially, you want this curve to be like just a straight line. But you often don't get that. You get this other curve, and the values that are changing here are just a threshold value. So the output from the neural network is actually a value between 0 and 1, like a continuous value, and you're just using a threshold to tell to classify when if the number is beyond this threshold, we're considering it an anomaly. So if you have a high threshold, you are only getting really strong predictions out. So you might have a really high precision, but you might not collect all of the anomalies. And the precision recall curve is like, kind of the same. You want the x-axis here is the recall, so how many of the anomalies that you're actually collecting in the end. And the y-axis is precision. So again, you want that curve to be as close to being a straight line as possible. Yeah, so that's the end of part one, where we have seen now definitively that in this case, self-supervised learning increases the performance. Okay, so I think we have a break now, 15-minute break.
Thanks, Spencer. Let's give a round of applause for the first part of this. So we're at a little bit behind schedule right now, so we'll still take a 15-minute break. So 10:45, we'll be back just before 11. Please be back by 11. Thank you. Okay, everyone. Thanks for the patience and the break. We're going to come back and continue our second half now. For those having problems getting a GPU allocation, apologies about that. We will be speaking with the CoCalc platform folks about ensuring better availability of those next time. But I want to kick back off with Spencer. We're going to just he's going to actually run on his local laptop, and you'll be able to see what his local GPU laptop setup can do. And for those who are having trouble with the allocation, we'll follow up with you and just let us know if you'd like a demo another time when we can have enough GPU servers. So apologies for that again. All right, I'm gonna turn it back over to Spencer. Thank you.
Thank you, Drew. Okay. One second here. Okay. So yeah, I lost my GPU allocation on the CodeCalc platform, which was perfect. And now I'm running everything. I had the backup, at least for using my my laptop with its onboard GPU for the rest of the tutorial. So I went through the part one steps already. And part two. So this is, yeah, part two is basically the whole workflow that I used for this project. From collecting the spectrograms using the ONC Python API client, and using the labeling app that I created for creating like a JSON file that associates labels for every single spectrogram, creating the HDF5 datasets, fine-tuning or training Samba model and fine-tuning. And then in my more recent work, I'm also making spectrograms from the actual audio files, the FLAC audio files. So this part also shows how to just download the audio data from ONC if you wanted to create your own spectrograms, because yeah, you can query the ONC API to get spectrograms that have been created on the ONC servers already, which is quick, or you can make spectrograms yourself, which is not quick. Okay, so yeah, you'll understand how to get some ONC data, see how the labeling works, and how to produce the data sets and train. Okay, so if you are following along, you actually need to get an ONC API token. So you would just need to click on this URL here to go to your profile on the Oceans 3.0. 1 second, I will bring that up. So if you haven't signed up yet for an Oceans 3.0 account, this will take you probably to a sign up page. So make an account. And once you have made an account, it should take you back to your profile page. And then once you're there, just go to the Web Services API. And you will have your very own API token, which you can click on this button to copy it. And if you go back to your notebook here, you can paste it in here. So I'll just show that process again. Click on this link here, which pulls up the profile page. You will need to make an account if you haven't already. From here, you just click on the Web Services API to get your API token. And this allows you to download data using the ONC Python client. Okay. And yeah, just paste it in here where it says default token. put it in between the quotes, and execute that cell. Okay, so this is, we need to download some data from ONC. So I have some code in the GitHub repo that makes this process a bit easier, where we can see which hydrophones are currently active and see how long they've been deployed for like which dates. So running this cell does that. It goes and collects all the deployments of all the hydrophones that have ever been deployed. It finds that there are 34 active hydrophones and goes and just collects kind of the metadata about all these hydrophones. Ooh, I can't really see my scroll bar on the right. I'm just gonna, okay. Yes, you can see some information that's printed out at the end of that, but the next cell presents it in a nice tabular format where you can see the location of the hydrophones. The position column just corresponds to, sometimes our hydrophones are in an array, so there's like a collection of hydrophones all hanging out together. Usually it's like 4 hydrophones, so hydrophone A, B, C, and D. They're all at this Barclay node location. There's device IDs for each one. You can see when it was deployed, and all of these ones I've picked to be that they're currently active, so they don't have an end date. They're currently operating. You can see what the depth is, the latitude, longitude. So yeah, lots of useful information for these active deployments. And so you can just choose a hydrophone using the device ID. Choose one that you think it might be interesting. I have personally chosen, where is it? Yeah, Endeavor. So this is at a very deep location in the ocean that is very interesting and relevant for ocean science. And yeah, so it's about 2,200 meters depth. So it's a very quiet environment, which you will see in the spectrograms. But you can choose any of these. And by the way you do that is just replacing this device code with the one that you're interested in. And the start date, you just have to make sure that it is after the start date displayed in the table. So yeah, for the Endeavor one that I'm using, it was deployed in 2023, September 8th. So I just chose the date that was somewhat after that. And then you can choose how many days after this date you want to collect data for. So I'm just collecting for 3 days. In practice, you want this to be probably at least a year, so you can sample different seasons to kind of get this more generalized data set to train on. But just for the purposes of this tutorial, I just chose a small number of days to make things quicker.
Years over a terabyte.
Yeah. Yeah. Well, so you can choose how many spectrograms you want to download. In addition, so this spectrogram downloader that I've created in the GitHub repo, it downloads spectrograms with a sort of a sampling schedule that so if you define the number of days to be 365, it'll choose days throughout that period that sample like different days of the week, different times of day, to just get this like very general sample, so we're not biased towards any specific time or a specific day. And in all cases, you will get approximately the target number of spectrograms. So you're not always going to get like a terabyte of data if you choose 365 days. Yeah, and this sampling schedule is something Alex Slonimer created. So thank you, Alex. Yeah, and I'm downloading the audio with these spectrograms. You can set that to false and things will run more quickly, but when we're labeling spectrograms, it is oftentimes very useful to listen to the audio as well. Because sometimes you can't necessarily see the anomaly in the spectrogram. So this will take about a minute to run through. So it submits a bunch of requests to the ONC API in parallel, and then it keeps polling those requests to find out when the data is ready to download. Once the data is ready to download, it downloads it all. Yeah, so should be estimated processing time 35 seconds. We'll see if that's true.
So Spencer, we just need to, if we wanted to change the hydrophone from what you had set the default, we just change the name at the top and then make sure the dates is within the date range of when it has data, and that's it.
Yes. So the question is just confirming how to choose your own hydrophone. So yeah, you just change the device code and you can change the start date. You just have to ensure that the start date is later than the start date of when it was deployed, or else there will be errors. You will not get the data. And this comment is not totally true. You should not do like 0.4 here. So just keep that in mind. Okay, so it's taken a minute and a half, but it should be almost done. So yeah, it gives you some information about like which days we're sampling from. Yeah. Great, some errors, of course. Okay, so we're downloading some FLAC files. Are you also downloading data? Yeah, cool. Yes?
So if we pull the data from ONC, we get the map file, the system code. If you wanted to run it on your own kind of something that would you pre-process that in MATLAB to get the map file, or like how would you get to that stage to run it?
So the question is, if you have your own hydrophones that you're working with and you're not necessarily using the ONC API, because the ONC API gives you MAT files, how would you use your own data? And so, yeah, so I think the labeling app that I have made, it accepts PNGs or MAT files. I can definitely expand it to include more file types. And then to make the actual like H5 datasets, it doesn't matter what format goes in. All that matters is that it's a matrix of numbers, which I get into kind of later on. So the MAT files, yeah, basically the data doesn't need to be MAT files for all this to work, because a MAT file is just a matrix of numbers. So as long as it could be like a NumPy array or whatever. Yeah. Yes.
I guess like that's maybe like an internal thing, but we probably also shouldn't use. You should use like the archive file service and access the files directly instead of like the data product delivery service that just like creates like a bunch of unnecessary problems and stuff.
Yes. Yeah. I think for the FLAC files, I am using the archive service. I believe I am. But
well, because like it says, you know, like this whole process that you have to wait for the files to be listed, like in the case.
yes,
Okay.
I'm using the archive files, but
There's no reason to be.
so actually the map files do need to be generated on the fly because of the specific resolution that I'm downloading. Because the ones that are available in the archive are at a lower resolution that I wasn't using for this project. Yeah.
So you're basically using ONC servers to do some bunch of processing.
Yep. Yep.
So if somebody had downloaded ONC data a while ago, those file types, they can still not be able to run your tool because they might not have the right requirements in that files.
The question is if someone has downloaded ONC data in the past, which used a different method of storing the data, will this still work? And I think the answer is it will still work.
I don't know finished, so
Oh, great.
yeah. Here's some.
I'm gonna see if I have enough data to work with. User generated. No. ONC destruction. Yeah.
Oh, yeah, I just finished.
Ah, great. Wow, we got a whopping 38 map files. Cool.
The numbers are not the same.
Yeah, good question. Usually they are. In all the other times I've run this cell, they were the same number. There must have just been some API errors maybe, or I don't know. Yeah. Okay, but we have some data. Great. So we can continue. This cell where we're generating spectrograms from the FLAC audio. This is, if you wanted to create your own custom spectrograms with a specific resolution in time and frequency. Because the resolution with the kind of standard ONC spectrograms are not necessarily, the resolution isn't high enough for some types of signals, like maybe whale calls. So that is a case when you would want to probably increase the resolution in probably both time and frequency. And I have some information here about how you do that. And you can even like have some target frequency bins and target time bins, and it goes and calculates the parameters for you. This takes a while, longer than downloading the data. So I'm going to skip right now making those custom spectrograms and just use the map files. If you in the future, if you have your own custom spectrograms from this, you just switch this to true. But I'm going to use just the map files. Yes, question.
Other than C2OK sample rate per pound.
Yes, the question is, can the model handle different sample rates? The answer is yes. Yeah, the only thing the model cares about is the data being in a matrix representation. I think it's no, I don't think it's required to be a square matrix. I think it can be, I think the X and Y dimensions can be different. But yeah, the only thing that matters is that your data can be represented as a matrix of numbers. So it does not matter what your sampling rate is. Okay, so this is the labeling tool I made for Herminio to label the spectrograms. It's a pretty simple interface. You can change the color map, so you can kind of pick out different features more easily. You can change to a logarithmic y-axis to pick out other features more easily. You can click on individual spectrograms to get a better view. You can like zoom into specific features. And then with all of these, you also have ooh, can't access it. 1 second. Okay. I think there's an issue going on with my. Yeah. No. Hold on, I'm gonna bring this over to my laptop screen instead of the TV. Oh, okay, I see what's happening there. Okay, yeah, so for all of these, you also have the audio playback. And for Endeavor, the audio files are extremely quiet. You need to like boost, you probably need to use headphones and increase your volume to maximum. And even then, it would be quite difficult to hear the signals because a lot of them are, very low frequency. That would be difficult for your ears to hear. Yeah. Okay, I need to bring this over to my laptop screen again. 1 second.
So maybe you should have a control to speed up the sound.
Oh, yeah. Control to speed up the sound would be good. Yes, that's a good idea. And to also like boost the decibel level and yeah. Those are definitely in the plan. Oh yeah, so to use the labeling app, that's right. I need to label some of these. So I have this whole hierarchical classification. It's a little squished on this screen right now, but you can see these like main categories where there's like biological signals, geological signals, instrumentation, human created signals. So most of these just have kind of nothing going on in them. Yeah, so but I'll just show you what it would be like to label. You can even type. So if it's like a vessel, I would just type vessel here, and then it goes up to vessel automatically, and you can see all the different kinds of vessels we have in this hierarchical scheme. So let's say military ship. And you can also have like multiple labels for every spectrogram. So I can clear this and go to, say, instrumentation. Yes, we can expand that and go to like malfunction. So we have data gaps, frequency dropouts, things like that. So yeah, you can pretty easily label all these things. I'll just do a couple more. Let's go with like data gap. There we go. Okay. So yeah, and then you get about 25 spectrograms on a page, and then you can go like to the next page, and there's a whole like cache mechanism in the back end that preloads all the data. So it all happens pretty quickly to switch a page. Yeah, so that's what Herminio used to label thousands and thousands of spectrograms, which took him a while. And yeah, there's like some somewhat useful prints that happen. I'll just go down past that. And then, so all that, as you're clicking the labels, it is populating a JSON file JSON file is just a kind of a nice format. It's like human readable. And this is the format. So you have the name of the file and the different labels given to the spectrogram. And yeah, so the hierarchy is displayed here with these greater than symbols. Yeah, so in the end, we had like a JSON file with like 7,000 of these kind of inputs into the JSON file, and then that when you create your H5 file, after that, this is the file that's used for that, and in the one of the end stages of this project. The JSON file is also going to be used for like annotations into our Oceans 3.0 system so that we can easily just ingest annotation information into the system. Yes.
Is it kind of like the labels apply to the full 5-minute file, or are you selecting very specific portion?
So these ones are applied to the entire. So the question is, are the labels being applied to the entire spectrograms? Because it is a 5-minute spectrogram, and the anomaly doesn't always happen in the entirety of the spectrogram. And the answer is that it's applied per spectrogram. We definitely would like to have like location information like start and end times and start and end frequencies. That's definitely a later stage project. Yeah, I have plans of like possibly creating some sort of like citizen science interface where people can go and label spectrograms themselves. And that would be very helpful. And yeah. So in this case, it's just the entire spectrogram. And Pia, did you have a question as well?
Would changing the sample rate affect the model performance? For example, if the sampling rate is increased but the FFT size is kept the same, then the frequency bands will be wider. For example, tonal sounds could get lumped together.
Okay, so the question is, if we change, like if you're using data that has a different sample rate, and you're using certain parameters that like might decrease the frequency resolution and the time resolution, will this affect the performance of the model? And yeah, definitely it will. And I don't have the answer for like the optimal parameters for the best performance for like a general case. It's always going to depend on your specific use case. If you're looking at signals that are very, very short in time and very limited in frequency extent, then you're going to want specific parameters that like very easily show those signals in the spectrograms. For example, I'm working on a project that's trying to identify fin whale sounds in spectrograms. And yeah, I needed to create my own spectrograms that are not 5 minutes long. They're like 40 seconds long. And they have increased increased resolution in frequency and time. So that I can like really, really clearly see those signals, which helps a human annotator, but then it also helps a machine to see those signals. So yeah, the parameters you use are always going to depend on your use case. And the performance of the model will change. So you just kind of like, you have to play around with the parameters, train a bunch of models, see which ones you get the best performance with, and stick with those parameters.
Are 5-minute spectrogram or the label associated with certain time span and frequency?
Okay, so that's the same question that we had in here. It's just is the label we give the spectrogram for the entire 5-minute spectrogram, or does it have information about time and frequency? And yeah, in this iteration of the project, we're just doing the entire spectrogram, but in later iterations of this, and I'll always be like updating the GitHub repo. We will hopefully also have location information in the spectrogram. Okay. So this cell just kills the labeling app because it's not really supposed to run in a notebook. It's supposed to run in your browser. So this kind of messes things up if you don't kill it.
Oh, you're supposed to? That's not working for me, so you're supposed to?
Yeah, you're supposed to kill the process.
Which one?
The dash app of the labeling app.
Okay.
After you've labeled, yeah, after you've moved on from labeling. Yeah. Yeah. Oh, and yeah, in the GitHub repo, there's like instructions on how to run this labeling app on your own machine, and it's all browser based. Okay. So we take that JSON file and we create some vectors that describe the kind of anomaly that is in each spectrograms. So it's called a one hot vector. So it's again like that binary vector that I talked about before, where each position in the vector corresponds to a specific anomaly type. And if there's a 1 in that place, it means that it has the anomaly. This is just a representation that is used for like machine learning purposes.
Question.
Yep.
But the anomaly types are nested in sometimes like you have a hierarchy there where like sometimes you can identify that a vessel and sometimes you go deeper.
Yeah.
So in this binary vector, each index is like is I guess a combination of where it is in the hierarchy. So like each place in the hierarchy is a unique value that you can.
Yeah, so this is like a work in progress because right now I've mostly just been working on anomalous or not. So this yeah, the representation, it includes every spot along the hierarchy. And I am working on multi-class classification, so knowing exactly what type of anomaly. I haven't yet decided if it's going to be useful to have all of that hierarchy available to predict or just the end of the hierarchy. I think it probably makes sense to have just the end, but yeah, I haven't fully decided on that yet. But for just binary classification, it doesn't really matter how you represent it. Because yeah, with the binary, we just collapse all of that into just a 1 or a 0. Okay, so then we create an H5 file from the label spectrograms. So yeah, this just shows how to create the final data set that's going to be used for ingesting the data into the model. So this is if you're not using mat files, this is something you would modify. The important part is just getting the data into the H5 file. And like you don't even necessarily need an H5 file because you can create your own dataset class. You can create your own data loader class that's specific to your use case. I just like using H5 files. They're very good for this particular setup. In like almost all machine learning setups, I have used H5 files. They're really good. But yeah, you can always define your own dataset class, which defines how PyTorch can access your data. And then the data loader class uses that data. So I think really you only need to define a dataset class for your custom data. And that's what's happening here. So I'm going through the mat files. I'm loading the spect data, which is just the spectrogram data. So that's the matrix of numbers. I am ensuring they're square, which is actually not necessary, but that's what I started with in this project. I retrieve the labels from that JSON file. And I collect all that matrix spectrogram data and the label data and create the H5 file with that. So as long as you can just get your data represented as matrices, then you can easily create this H5 file with whatever data format you have. Okay, so we have the H5 file, which is a very small data set. It's 38 samples. So it's not gonna give any decent results at all. But I'm just showing for brevity's sake how to do this with this very small data set. But ideally you want a lot more. So yeah, I just show I take that big pre-trained self-supervised model that we used earlier to fine-tune on that small data set that I created. So we're doing the same thing here. We're just fine-tuning the Samba model on this very small data set. So yeah, we use this pre-trained backbone. So it was pre-trained on I think it was like 8,000 spectrograms or something, 9,000. Yep. And so this just shows how to set all that up, how to use the H5 file, how to make the custom dataset class. So if you're not using an H5 file, this is what you would change. So you would point it to where maybe the directory where your data is stored, and then just how to get the label, how to normalize, how to get the item. So this is how I'm retrieving the spectrogram from the H5 file. And you would want to change this for your specific setup if you're not using an H5 file. And then it creates a training set, creates a validation set, builds a split, creates the custom data sets, creates the custom data loaders. And then there's a bunch of arguments here that you can change depending on your use case. And these are all explained kind of in the GitHub repo where all these things are defined. So this is just instantiating the fine-tuning model, and this is training it. And I think it doesn't take very long because it's only 38 samples. And I mean, the output that we get out is we get 100% accuracy, I guess. Yeah. But that's just like small number statistics, I think.
Did you use the labeled stuff that you actually showed labeling?
Yeah.
Reset out. You only did like 3.
True. Yeah. So there's only like 5 labeled things here. Yeah.
It says 7. 1.
Yeah. So I think that's the validation set. We have one anomalous sample, and we're getting that one correct.
So just to clarify, you brought up that UI earlier that had all the spectrogram images and whatnot.
Yeah.
You have to manually label them yourself before continuing?
So the question is, I showed the labeling app prior to this, and do we have to label things before getting to this step? And yeah, you do in this specific tutorial notebook. But if you already have like a data set of, say, whale calls, and you've already curated this data set, when the whale calls are, all you need to do is download the data and create the JSON file that, using the same structure. of the file name and the label. And so you don't need to use the labeling app because you've already done it. But if you don't already have labeled spectrograms, you need to use the labeling app. Yeah. Yes. Okay, so we fine-tuned it. And I think it ended early, unless I defined it to be 8 epochs. Yeah, okay, so I defined it to be 8 epochs. Great. So we predicted 1 out of 1 anomalies. We did a very good job. Okay, so then the last thing, so yeah, we're at 11:45. The last thing here is just showing how to pre-train the Samba model from scratch. So this one is actually quite computationally intensive. The inference, like once you have the trained model, running predictions on data afterwards, that's not too computationally intensive. But the training procedure for the Samba, again, is like patching, turning the images into patches and masking some of them and doing these reconstruction tasks and these location prediction tasks. And that is just more computationally expensive and takes a while to train. But yeah, our data set is like 36 spectrograms, so I can try to see how this works. But yeah, again, this is just showing how to like set up the unlabeled spectrogram data set. In this case, unlabeled just means like your normal non-anomalous spectrograms. So yeah, so that your model learns what normal looks like, and then anything that stands out from normal will be very easy for the fine-tuned model to pick out. Question? Okay, so the question is, what reconstruction accuracy should you look for in your while you're training? And it's just the best performance you can get. This is kind of like with machine learning. You when you make a model, there's all these hyperparameters that you use to construct a model, like the number of layers, how many patches in this case, how many patches you turn the spectrogram into. Even like in creating the data set, there's all those parameters about like with your fast Fourier transform, like what sort of frequency resolution and time resolution you want. So there's all these parameters that affect the final performance of your model. And in any machine learning application, basically you just run a bunch of experiments with all these hyperparameters changing, ideally in some sort of like intelligent way. But you can also just do like random grid search in your hyperparameter space. And yeah, you train all these models and then you just use the one that gives you the best performance on a test set that you hold out that it never sees. So it's not necessarily an easy process. And I usually I use the resources available on the Digital Research Alliance, which lets me train like hundreds of models at the same time. And I can't do that on my laptop. It's really hard to, I mean, you can, it just takes longer. But yeah, that's how you set these problems up. You don't know what performance you're aiming for. You're just trying to get the best performance that you can. Yeah, so for the pre-training, yeah, I just show how to create the dataset class, how to get the items from the H5 file. So again, this is where you would, if you're not using an H5 file, be changing things. There's some model size options. I'm going with tiny. The larger models will probably give you better performance. So yeah, that's one of the hyperparameters that you can change when training these models. Yeah, so just going through creating the data sets, creating the data loaders. These pre-training arguments. There's different pre-training tasks, which again is explained in the GitHub repo. I'm just using this joint objective that uses both the self-supervised tasks, but if you just wanted to use one of them, you can change that. Yeah, let's see if this works. I think when I was testing this yesterday, even with 38 spectrograms, it was causing my fans on my laptop to blow wildly. So yeah, it's a pretty computationally intensive process. So usually on my laptop, I run really small experiments just to make sure all the code is working, and then I move everything to the Digital Research Alliance resources where I can boot up like massive GPU compute servers. Yeah, so even with this small number of spectrograms, it's taken a while, but yeah, the fully last thing is that I just show in this last cell what these self-supervised tasks look like in the code, and I give like a richer look into, oops, I give a richer look into what the self-supervised tasks are doing. Oh my God. Oh, 1 second. Sorry, I got kicked out of Zoom, but I'm back. Sorry about that. Okay. So yeah, the last cell just gives some better intuition for how the self-supervised tasks are working, how we're patching the data, and how we mask it, and how we run the location task and the reconstruction generation task. So there's a lot more information in here than in the repo, just to explain things. And this is, yeah, if you were working with your own data, like if one-dimensional data, for example, these are the self-supervised tasks that you would change. And yeah, it's definitely not straightforward. You would probably want to use code that exists out there or use ChatGPT or something like that to help you with that. But like, yeah, for example, I used this Samba model that had a public GitHub repo and all these things were defined for me. And I just adapted everything to the problem that I had. Yeah, so that's it. If you're able to follow along, I hope that all the cells ran for you. And that you were able to kind of play around with some of the parameters. Yeah, the compute servers I'll be turning them off shortly. For those of you who got some. But yeah, I guess that's the end of the workshop.
Want to mention that OSC just has an opening for bioacoustics data analyst.
Hold on a second here. That's a great segue. Thanks, Martin. Martin's suggesting some things we might mention here at the end. Let's give another round of applause. Thank you very much. And again, let us know if you weren't able to spin up a GPU today. We can set up a side little chat for you and do a run through. So before we wrap up for the day, are there any last questions that anyone has burning, either online or in person here?
You could stop sharing so we can see.
I'm going to keep sharing.
Oh, you're gonna stop.
I will have to stop that. Right. Sure, email.
So what's it? What are you looking for?
1 second, please. My apologies. We're just changing it. We're doing a quick presentation swap here. We only have like 5 minutes left. If there are any other questions, please post them. Oh, yeah. The question was, will there be access to the notebook after this? And the answer is yes, the notebook will be available, is currently available on ONC's repo. As well, the presentations that were shared today with you will be made available as well. So we can do that. Okay. So this was intended to kind of go at the beginning. Sorry, let me do it this way. This was intended to go a bit at the beginning, but we do want to acknowledge and respect the Lokongan peoples whose traditional territory the university stands, as well as the Wasanic people with historic relationships to the land to the day. Apologies, we didn't have that up front.
Sorry. Yeah, I think we need to move this over here.
Yeah, that'll work. So just a word or two about Ocean Networks Canada. As I mentioned, we have a large infrastructure here. We started off as the Neptune network, which goes off the west coast of Vancouver out to the Endeavour Spreading Ridge and back, as well as Venus. Those two platforms merged together. And since then, ONC has been growing. These are a number of the communities that we work with. And just a couple of notes. We are one of the largest major research facilities in Canada, as well as a UVic initiative founded back in 2006. There's some additional stats. We have a lot of data. We have a lot of data products. We have a lot of users, and we'd like you to be one. These are some other data sources that we have that we offer, data products, which include CODAR, time series data, extensive video data, and other types of data sources and data products out there. So feel free to explore. This is our data management portal, which is linked there, data.oceannetworks.ca. And you can see a number of these. A couple of key pages I want to highlight are that Spencer used the API in his presentation today. So there's our API is based on the the Open API standards, which are documented there on our Open API page. There are a number of ways to request data via the Open API, right through our browser, right through our data portal, and you can see, for instance, ways to interact with this. It's just an example. The API is documented on our external wiki, which is linked at the top as well. And the GitHub repo that we currently use for Spencer's work also contains client libraries for Python and MATLAB, and we strongly encourage users to explore and use those and give us feedback as well. Finally, I wanted to say a few words about the Canadian Integrated Ocean Observing System, CEUS, as well as the Building Bridges project, for which ONC was a contributing partner. We are working to build an ocean AI community of practice across Canada, including a link, and we have a portal that's just now opening. It's still in beta, but feel free to get on there and join, and you can subscribe to more information from us. And then this is just a summary of some key links. Again, the Building Bridges page, Ocean Supercluster, our funders, we're very thankful for their input. And then, sorry, this scrolled off here a bit. We have a large amount of hydrophone and other types of data. So please use them, cite them in your next paper, and reach out via these links. I think that's it for today. Question? All right, we'll end with one last question for Spencer and then wrap up. Go ahead, Spencer. Do you want to read the question back again?
The question was, are there any anomaly types that are harder for our model to identify? And just any that are extremely rare, like some of the sensitivity issues. There are just not many of those samples in the training set or in the entire data set at all. So no matter what method you use, it's just going to be harder to find those ones. Yeah, so it's just any of the samples that have very low numbers. We still do decently, like the self-supervised does improve on that, but it still struggles.
Okay, that's it for the workshop. Thank you all for attending here in person. I hope you enjoy your very good cookies. And for those online, thank you for joining us as well. Thank you, Spencer.